Okay, so you can see here that I've done a population 1 and I've done a population 2. And I've just pulled out every 2. And I've got my homozygous dominant ones right here, my heterozygous ones here, my homozygous recessive here. Population 1, I've got homozygous dominant, heterozygous, homozygous recessive. And so you can see that's what it would approximately look like, and everybody's going to have slightly different because it's probability, right? All right, so we're going to look at the numbers now on the board. I'm going to bring this back around, and we'll talk about it. Let's see here. Okay, so I went ahead and counted them for you. And so you can see in population 1 I had 7 of these, 14 of these, 32 of these. Population 2 I had 30, 18, and 5. They will only have done one of the populations. And then it asks them in their student guide to figure out the genotype frequency and the phenotype frequencies. Okay, so for this, what we have to first figure out is how many total individuals we had. So we had 53 individuals here, and we had 35 plus 18. Yeah, mental math's not my thing. Oh, wow. 53 individuals there. That was uncanny. Okay, so we have 53 individuals. So out of those 53 individuals, 7 of them were homozygous recessive. So that gives us a frequency of 0.13, 14 out of 53, 0.26, and 32 out of 53, 0.60. And then the same thing over here, 30 out of 53, 0.57, and I'm rounding, okay, 18 out of 53, 0.34, and 5 out of 53, 0.09. So that's genotype frequency, and then it asks for phenotype frequency. Well, these guys are going to be yellow, right? So that gives us 0.39 yellow, and these guys will be white, so that's 0.60 that is white. And then over here, 91% yellow and 9% white. Okay, let me make sure you can see those numbers. Are we okay there? All right, I actually might move you around just a second. Okay, so move in a little bit. All right, so there's our percentages that they're going to figure out, and everybody's is going to be slightly different. Okay, but they're going to graph, or they're going to figure it out on there, and then at number 5 it asks them to reproduce. Okay, so this is very important. They have to reproduce with someone of their same population, because like I said, flowers aren't traveling up and down the mountain to mate with populations at the top and the bottom. They're mating amongst themselves. And so each partnership, they're going to have to go outbreed with some other partner. So they're going to take their beads, scoop it all back into their little cup. Oh, by the way, if there's an odd number of beads, just tell them to throw it back. Okay. So they're going to take their 2 cups. So let's say you have population 1 from over there and population 1 from over there. They're going to come together with their bowl, and they're going to dump their sperm and egg, do a little mating in class, into the bowl, mix it around so it's doing this little mating, and then just evenly divide it back between the 2 cups. There's going to be beads all over the floor. Just make sure they pick them up. All right, so they'll get their 2 cups, they'll go back to their tables. And everybody just is going to pick somebody, and hopefully you have an even number of groups. If you don't have an even number of groups and someone's the odd man out, you as the TA make yourself a cup of their population and mate with them. Mate, that sounds bad. Mate, yeah, okay. All right, so once they've done that, number 6 has them do it again. So they're going to do the same thing. They're going to lay it out on the board. They're going to get new numbers. Because what we're trying to answer is, does the dominant allele get more frequent over time? If we keep mating within the same population, does the dominant allele get more frequent over time? All right? So they do it a second time. That's number 6. And then they're going to mate again. Again, they have to mate within their same generation, but tell them to mate with a different partnership. Okay, so just find another person who's a number 2 like you and mate with them. Okay, just so that we're showing them that, hey, it's not just because we're mating with the same people. You can mate with anybody as long as it's in the same population. So 2s mate with 2s, 1s mate with 1s. And they're going to do it again. Figure out all the frequencies for number 7. And then number 8. So have them do number 8 on their own. They're going to construct a series of graphs. Now, I would let them do this on their own. Just say, hey, however you want to represent it is fine. They should be doing it on their whiteboards, okay, so they can show it to everybody. The easiest way to do it is a bar graph, but don't tell them that, because part of the objectives of this lab is to learn how to graph. All right, so they're going to do, am I going to check something on this? Just had to make sure it was recording. Okay, they're going to do their graph. So my graph might look something like, and they'll probably do two graphs, one for genotype frequencies, one for phenotype frequencies, or you could do it all on the same graph. And so here's big Y, big Y, big Y, little y, little y, little y, and they're going to have their 3 iterations of it. So in generation 1, we were, so if this is at 50%, right? This is at 100%. Generation 1 for this particular population had only about 13% of these and 26% of these and 60% of these, right? That would be generation 1. Then they did it again. Oh, and then over here we're at 40. This is 50. So they're at 40 for yellow, and then white ones, they're at 60. Okay? So that's generation 1, and then they'll just graph it on the same graph. Here was generation 2, and maybe it was slightly different, right? In generation 2, it might have looked like that, right? And they're going to get different numbers depending on their, I guess that should go down, that goes up. Depending on the probability, right? It's all just probability based. So there's generation 2 and then generation 3. They might have gotten similar numbers. Okay. But what they should see, so there's generation 1, generation 2, generation 3. What they should see is that over time, there's no rhyme or reason to the change. There might be slight changes here and slight changes there, but it's just due to probability of picking the beats, okay? And when they share it with the other people, when everybody shows their graphs, they're going to show, oh, mine slightly went up, mine slightly went down, mine went up and then down. And you're going to ask, is there any pattern? Is the dominant allele, is the yellow allele getting more frequent over time? They're going to answer these questions though first. So A, it says, what pattern do you see in genotypes and phenotype frequencies across time? What they should see is that it doesn't change. Excuse me. B, how do your patterns differ between the two populations? So that's something to talk about. Oh, let me go back to the first one though. When you have the group discussion about A, and they see that, it's not really changing. If they do see changes, say, hey, why did you see those changes? And people will be able to say, it's random, it's probability. Yeah, it's just probability. There's no reason for the changes. It's not going up, it's not going down. Why doesn't it change? What I'd like to illustrate is that everybody in here took from the same bucket, right? So if I pull, I don't know if I need this cup. If I pull a cup of beads out of here, and then I pour it back in, and I shake it around, and I pull it out again, simulate, here's the population, then it mates with everybody, we pull it out again, we pull it out again. Is there any reason to expect that these beads are somehow going to get more yellow? Like, are white beads spontaneously turning yellow? No, of course not, right? So why would you expect over time for the yellow to become more frequent if we're just pulling out gene pools, putting it into people, and then they're mating and putting it back into the bucket, and then we're pulling them out again, and then they're mating and putting it back into the bucket? There's no reason to expect that somehow these beads are going to turn more yellow over time, right? And so that's the beauty of this, is that there's one population that's mating over and over again. And so as long as that's happening, now we're going to talk about one that doesn't, but as long as that's happening, there's no reason for it to change. Okay? So that's a point you want to drive home. So for part B, it says, what's the difference between the two? So you might look and say, kind of estimate. Can you estimate what percentage yellow to white these are? Now when I made these, they're looking a little bit mixed up, but when I made these were about 75% yellow to 25% white, and these were the exact opposite. 75% white, 25% yellow. So the question is, if they really are just the opposite frequencies, why do we see in population 2 oh, I've got these backwards. Oh my gosh. You guys, that's terrible. This is population 1. It's on my table as population 1. I counted them backwards. That's funny. So anyway, why do you see amongst this population, why do you see that it's 91% yellow and only 9% white? Which makes sense by looking at this population. It looks 91% yellow. But why, if this one's got an equal number of white beads as that one had yellow beads, why is it only 39 or 60% of the most frequent color, the white? Why is it only 60% to 40%? Why isn't it 90% to 9%, just like that one is? Why isn't it 90-10 like this one? Okay, and let them stew over that for a second. Hopefully they can see that because these heterozygotes actually group with the other color, because it's dominant, we don't see the same pattern between them, even though they're the opposite distribution. I am so sorry, did everybody catch that? The one that's mostly yellow is population 1. I just labeled them on the board wrong because I wrote them from the desk. Okay, so that's something you want to point out for B. For C, it says, what conclusion can you draw from your data regarding the effect of dominance? The effect is nothing. Being dominant does not affect the frequency, okay? Now we're going to talk about cases where frequency does get affected, but in this case, being dominant doesn't somehow make it take over the world, like people seem to think, right? And so some of the examples I like to use is polydactyly, having 6 fingers on your hands. That's a dominant trait. But if you look around, 99.9% of the population is homozygous recessive. And we only have 5 fingers on our hands and 5 toes on our feet. But that's a dominant trait. Same thing with achondroplasia. Achondroplasia is a type of dwarfism. It's the most common type of dwarfism. And it's also a dominant trait. But you don't see it in much of the population. It is the least frequent trait. And so most of us are homozygous recessive. So just because a trait is dominant does not mean it's going to be more frequent. Huntington's is a dominant disease, but it's not the most frequent phenotype, right? Hopefully, cross fingers. Okay, so there's a lot of things that are dominant that aren't the most frequent, because dominance has nothing to do with frequency. So that's the point you're driving home, all right? Okay, so we're going to move on to part 2. I'm going to pause this for just a second.